All right, well, welcome to day 2 of Trig. We're pretty much just going to pick up where we left off and keep running with it. Last time we basically just started talking about angles and how we deal with angles and how we measure them. Some big things I want to remind you that angles, what we're really looking at is rotation. The sooner you can get into your mind that angles are about rotation, the easier the rest of trig is going to be. Okay, so when we map out an angle, and you'll see me do this all the time with my hand, I'll pivot it, I'll rotate it, because that's how I think about angles. It's a rotation. It's a spread. It's not a distance. It's really a how far are we going from one ray to the other, or one line segment to the other. So it's all about rotations. The values of angles, if we're in degrees, they come from portions of rotation, like what portion of 360 degrees did we do? And the same thing in radians. So what portion of a rotation happened? What fraction of 2 pi have we done? All right, so that's the big takeaway, hopefully, for you guys, that angles are all about rotations. So we talked about a lot of other things. We talked about the quadrants. We talked about some terminology, right? We got our initial side, we've got our terminal side, we've got standard position. We've talked about what it means for a positive angle versus a negative angle. Only difference there was the direction of rotation. Positive is counterclockwise and negative is clockwise, right? But other than that, it's exactly the same. So we spent quite a bit of time talking about angles. And I want to talk a little bit more about them and just some other things that happen because of the fact that they're rotation. And then we'll start looking at triangles. I mean, this is trigonometry after all, right? Triangle measurement. We should probably see how how the tools of trig, the trig functions are defined in terms of triangles. So that's my plan for what we're going to do. But at the start of class, I always like to open it up to you guys to see if there's anything you'd like to talk about from the homework or any of the concepts from last time that were still a little bit confusing. So if you've got any questions along those lines, go ahead and speak up or type them in the chat box. Anything today? We're doing all right so far? All right, well, hearing nothing and seeing nothing, I'm going to assume everything is going on okay so far. So, so yes, Jack, today we are going to talk about velocities for sure. Yeah, that's when I want to mention some of the things that happen because it's rotation. Velocity is one of them, because if we want to talk about how quickly something is rotating, obviously that's going to lead to velocity. So yes, we're going to talk about velocity and other things like area of sectors and stuff like that. So we're going to finish up 4.1 before moving into 4.2, or sorry, 7.1, moving into 7.2. Other questions at this point? All right, well, hearing none and seeing none, I'm going to go ahead and hop up to the whiteboard. So I'll be right back. All right, so let me just remind you a little bit about what we did last time, some kind of important things regarding angles that I want to make sure we're all on top of. So first of all, like I mentioned before, remember that what we're really doing when we look at angles is we're looking at rotation. We're looking at how far are we rotating a line, segment, or array to turn it into the other line, segment, or array that makes up the angle. So when we've got an angle, we'll put it in standard position. So it's going to look like this. Standard position, again, the vertex where those rays come together is at the origin, And the initial side is on the positive x-axis. So I'll always draw the little curvy arrow showing us the rotation, showing the direction of the rotation, since that matters, plus or minus. So this is a positive angle, and it would be how far, how much of a complete cycle do we rotate to get from the initial side to the terminal side, right? So again, the names of these, we have an initial side and we have a terminal side. And this point was the vertex. Okay, so that's the geography of the angle. So we always go to standard position when we draw them. So here's an example of the angle. So it's rotation, 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 rotation. The other big thing, the other important thing that we need to know here are the units of measurement. And we talked about last time that there are two ways that we measure these. The one is degrees. And this is what you're probably most familiar with. Right? So degrees, and the kicker to these is that there are 360 degrees in one rotation. And then the other one was radians. It's the other useful one. And radians, if there are 2 pi radians in one rotation. And on the surface, it feels really weird. 2 pi, right? Like, what the hell? But as we talked about last time with the definition of radians, it makes sense that it's 2 pi. So again, let me remind you how radians are defined, right? 1 radian is such that if we were drawing a circle here, if we chose some distance out here, some radial distance, and in fact, let me just remove the arrows so that this is a line segment. Do my best to make it equal length, right? If we were to follow this end, this purple point, it would draw along a circle, right? It would follow along a circle. And the way that 1 radian is defined, 1 radian is such that the arc length right here, if that equals the radius of that circle, then this angle that I'll call theta is equal to 1 radian. Okay, so basically the idea behind radians is that if you want to know how big your angle is, imagine you're just walking along the circle, and you've got your favorite app that's keeping track of how long you've gone, right? Or you've got a Fitbit on your wrist or something like that, right? And it's keeping track of your distance traveled. If you were to just divide by the radius of the circle, the distance divided by that radius is what your angle is. All right, so radians are a way of knowing how far you've rotated by looking at how far you've moved. And you can probably see how in an applied situation that can be useful. Like, think about all the things that move around in circles, right? There are lots of things. Like, think about on your bike wheel, right? Your car tire, the earth-ish, right? There are lots of circles out there in the real world. And so if we're moving along the path and we can keep track of how far we've gone, it's going to be pretty easy to come back and get what our angle was by keeping track of that distance. All right, so it's a weird thing, I know, but that's how radians are fun. So check this out. Because of that relationship, we actually have a formula that we can write in terms of the arc length and the radius. All right, so let me go to another generic one because I've already kind of said that this was 1 radian. But let's just go to a generic piece of pie here. That's got a radius of r. And the arc length, we're going to use the letter S for that. That's pretty standard. That's not just a Bruceism. Pretty much everybody you see will use S to represent the arc length. And then, of course, we've got our theta right here. Well, the way that theta is defined in radians, this is important. Okay, so in radians, not in degrees, but in radians, that angle, it again is just the arc length divided by the radius of the circle. So theta is just equal to S divided by R. I remember this as S equals, and so this is what I recommend you remember, is that S is equal to R times theta. But if you remember it as theta equals S over R, it's the same thing, right? Algebraically, it's the same. It's just written in a different form. All right, so this is another reason why radians are really kind of nice, is if you want to know the arc length of a circle, boom, it's fast. It's just S equals R times theta. Okay, so that's where we got. I gave you a little bonus today, right? But that's where we got to last time. So now let's just pick this up and keep running. So there's clearly now some relationship between the distance traveled on a circle and the angle that we sweep through. And that should make sense. Like if you look at this formula, you actually just think about it, it makes sense that it's written this way. So S, this is the path that you travel on a circle. R is the size of the circle, and then theta is the angle that we're rotating through. Okay, well, suppose that you're on a bigger circle versus a smaller circle, and you were to go through the same rotation. Let's pick a rotation. Let's pick a quarter of a rotation. So in standard position, I'd be going from the positive X to the positive Y. Okay? So we're just going to do that much rotation. If I were to do a different circular path, different size circle, I'm going to have different length that I travel, right? Like, this is what I'm talking about. Suppose that I do a circle, a small circle here, but I do a quarter rotation. So we'll make that one green, and then we'll make a bigger one that's black, bigger rotation. Right, so it's the same quarter turn, but we're on a larger circle. Clearly, that black path is longer than the green one. Well, that's what this is saying. You change your R, you make your R bigger, your arc length is bigger. If R is smaller, your arc length is smaller. So that's a, yeah, duh. It should definitely be that way. And then notice that it also says that if your angle is larger, then your path is going to be larger. Well, let's take a one size circle. So let's take the circle that was black. That was a quarter rotation. Instead of doing a quarter rotation, let's say I do a shorter rotation. So I'm only going to go, let's say, out to here. So we've got the same radius, but the purple path is much shorter than the black path because we did a smaller rotation. Right? And that's what this is saying. In the language of algebra, we say that these vary directly. I don't know if you remember variation. You have like inverse variation, direct variation. But the arc length varies directly with the angle, or varies directly with the radius. All right. Well, anyway, so clearly, we can see that you change the R, you change the theta, you're going to change your arc length, but you got this nice formula. Okay, now, there are actually some nice applications to this for things that are moving around in circles. And so this represents a relationship between distances. Let's look at a relationship between speeds or velocities. Now, I don't know how much you know about this stuff. So let me just bring this back a little bit. So velocity. I gotta, since I'm actually wearing my hat today, because I forget who, I think it was Danielle mentioned all her Dodger hats, so I have to wear one of my Mariner hats today. Since I got my hat on, this is my math hat.
So I don't know if you guys know this, but I also teach physics. So I'm a mathematician and I'm a scientist. I kind of straddle both worlds, right? Let me turn on my physics, my science brain for a second. So we'll turn it. So now I got my science hat on. Okay. Velocity and speed are not the same thing. They're not. Out in the, out in the world out there, people call them the same thing. They use them interchangeably. But to scientists, velocity and speed are different. So speed, you guys all know the concept of speed, right? It's how fast you're going. We measure it in like miles per hour, feet per second, whatever. All right, so that's just how fast you're going. Now, velocity, it also has a direction entailed with it. So if we're going to talk about your velocity, you'd be saying, okay, I'm going 50 miles an hour that way. So if you just say you're going 50 miles an hour, you gave me speed. If you say I'm going 50 miles an hour in that direction, you just gave me velocity. Okay, so there's a slight difference between velocity and the speed to scientists. All right, now mathematicians kind of care about that. Yeah, but not really, right? So we're going to use them interchangeably, velocity and speed. But let's just think about how we calculate speed, right? So speed, it's actually going to be a measurement of distance divided by time. Think about the units again, miles per hour. So miles are distance, per means divide, hour is time. So you're looking at how far you travel over a given amount of time. Okay, now to make sure that we know what we're talking about here in terms of the trig, this is what we call a linear velocity. Because there are other kinds of velocities, but linear velocity just means, hey, you take your distance and you divide it by your time, not your linear velocity. All right, so imagine that we're moving around in a circle. Let's say we're just on the circular arc. So if we had a particle here that was moving, going in this direction, and it comes up to this other part, the distance it traveled was s. And so if we wanted to know its velocity, its speed, we would just have to take that s and divide it by time, right? So the formula for this on our circle is v equals s divided by t. Okay, and I'm just going to put here, if we're on a circular path. All right, so pretty easy. You just take how far you went and you divide it by t, by how much time it took, but your linear velocity. Okay, well, we also have what we call angular velocity. And angular velocity is the exact same idea, except instead of taking a distance and dividing by time, we're going to take our angle and divide it by time. Okay, so this is your angular velocity or your angular speed. So if we're not here, if we don't necessarily care about how far we've gone, but what portion of a rotation is, that's where we would use angular velocity. So you look at how far do we rotate, and we divide that by t. All right, obviously we don't use the letter v for that, because if v is linear velocity, we need something else for angular velocity. So for angular velocity, we use this guy, which is not a w. It's not a w. I know it looks like a w, it's not a w. What it actually is another Greek letter. This one's omega. So that's the Greek letter omega. It's the last letter in the Greek alphabet. Some of you might actually know omega. I think it looks different. And that's because that's the capital omega. This is the lowercase omega. The capital omega is the one that looks like a horseshoe. Looks like that. So if you've done any kind of electrical work, this is a symbol that we use for resistance. Right? So that's a capital omega. This is a lowercase omega. Just like how we have uppercase and lowercase for different letters, so do the Greeks. All right, so that one's the lowercase omega. Anyway, all right, so there's our angular velocity. What angle do we go through with respect to time? All right, so let's do this. Let's actually just look at an example and find some angular velocities and some linear velocities. Play around with this a little bit. Okay, so suppose that we're just going around in a circle, and we're on a merry-go-round, right? Like one of the, they don't really have them in playgrounds anymore because I think kids got hurt too frequently. But I used to love being on those, right? You just spin around in circles. So let's say you're on a merry-go-round, and that merry-go-round has a radius of 2 meters. All right, so that means it's a little bit more than 12 feet across. So we have a radius of 2 meters. And suppose that we're sitting out here on the outside, holding on for dear life as this is spinning. All right, so somebody's timing it, and they see that one rotation takes 20 seconds. Right? So it just takes 20 seconds for us to go all the way around. So here's what I want to know. The first question is, what is the angular velocity? And then the second one's going to be, what is the linear velocity? And what did I say here? What is the angular and linear velocity? That's at this point. So for us out here at this point, what are our angular velocities and our linear velocities? All right, well, we're just going to use these formulas. So we'll start with the angular velocity. If we want to know the angular velocity, we need to know how long it takes to do a certain angle. All right, well, let's just think what we know. We know one rotation takes 20 seconds. So I've got a time that I can put in here. And so I need a corresponding angle for my angular velocity. So what angle are we going to use here for that 20 seconds? What angle do we go through in 20 seconds? All right, so let's see, I got 90-degree angle, 3/2 pi as a couple of choices so far. Well, here's how we need to think about it. That 20 seconds is one rotation. So that means we started here, let's say at the bottom of the circle. We're going to do one full rotation. So we start the stopwatch. You see us go around. We get to the bottom and we stop the stopwatch again. And that took 20 seconds. So what angle just occurred? Is it 90 degrees? All right, so Diego just typed in 360, so did Yair.
So it'd be
All right,
2
so a
pi.
lot of people give me 360. So it would be 360 degrees, right? Because we went one full rotation. All right, so it'd be 360 degrees, or how many radians?
2 pi.
2 pi. Good. All right, so if we're going to do this, it depends what kind of units we want. We can either use 360 degrees or we can use 2 pi radians. All right. Use radians. Use radians. The mathematician just said use radians. The scientist just said use radians. This is one of those places where mathematicians and scientists agree. When you do rotations, use radians. Use radians, okay? Because radians are dimensionless. Degrees are not. They're going to cause us a problem if we try to do this in degrees. So we're going to go with the fact that we do one rotation, so 2 pi radians every 20 seconds. So that's going to be pi over 10 radians per second. So that's our angular velocity. We could convert it to degrees per second, and that actually is totally fine. We would have done 360 divided by 20, and that would have been 18 degrees per second. But that's an angular velocity, because we're looking at the change in our angle with time. All right, so it was just that easy. Take your angle, divide it by time. So for linear velocity, we're going to do the same thing, except we need a distance. So let's use that same time. But my question is, how far did we travel? How long of a path did we travel? So come back up to this picture and think about that dot. So we're watching from above. We're watching this person at the end go around and come back to the same place at the bottom. So how much distance did they actually travel?
Wouldn't it be 2 pi times the radius?
It would exactly be 2 pi times the radius. Yeah, it's the circumference of that circle. How far did they travel? They went all the way around the circle, which is going to be 2 pi r. So this is going to be, in terms of the distance, I don't have a calculator handy, so I'm just going to do it as 2 pi times 2 meters. All right, so it's 2 pi r. So 4 pi, so that's going to be around 12.5 meters, something like that. Okay. So we're going to do 2 pi times 2 meters per 20 seconds. All right, well, that's going to end up being pi over 5 meters per second, which again, we could get a decimal approximation. Let me actually grab my calculator here real quick, because I know everybody wants to know roughly what that number is. And the mathematician is totally fine with pi over 5. The scientist isn't. He wants to know what the number is. So pi divided by 5. It's very Jekyll and Hyde kind of thing here. So we get 0.623 or 283. 0.628 meters per second. Okay, so that's a linear velocity. And that's what you think, like when you think speed, miles per hour, that's a linear velocity. So that's how fast that person is traveling. Okay, so that's the difference between angular velocity and linear velocity. It's just one is you're looking at angle over time. And the other one is you're looking at distance over time. All right, real quick, what if we hadn't been all the way on the outside of this merry-go-round? What if we'd been somewhere in the middle? And I'm not going to go exactly in the middle, but let's say that we're a distance of 1/2 meter from the center. So instead of 2 meters from the center, We're only a half a meter from the center. All right, so we're out on the edge, holding on for dear life. We got a friend who's closer to the center. Let's look at the angular and linear velocity for that person that's closer to the center. All right, so if we were to keep track of them, they would still go around in a circle. It's just a smaller circle. So let's calculate their angular and linear velocities. So I'm just going to do this in blue right next to these. All right, so we'll have an omega equals and a v equals. But let's look at the difference. So now let's do the velocity, the linear velocity. They're still doing that full circle in 20 seconds. But now the distance that they're traveling is 2 pi r, but their radius is smaller. Their radius is only half a meter. So this is going to be 2 pi times 1/2, which is just pi. So it's going to be pi over 20 meters per second. And so let's see, that's going to be 0.147-ish meters per second. All right, so before we jump back up to the angular velocity and finish the question, compare those two numbers. Take a look at those and check it out, right? Out at the outer edge, I know you probably don't have an idea of how fast that is, but it's 0.6 meters per second. And this one's 0.147. It's considerably slower. In fact, it's 1/4 the speed. And now I'm feeling like I didn't do that number right. I totally didn't do that number right. 157. That's better. But it's considerably slower. So the person on the interior part isn't moving as fast. Their linear velocity is much slower because they're still doing a circle in the same amount of time. It's just a smaller circle. All right, well, let's check out what their angular velocity is. Okay, so we're still looking at the 20 seconds. What kind of a rotation does that person near the center go through in 20 seconds? What angle in radians does that person do in 20 seconds? All right, so thanks, Diego. Just put in the chat box 2 pi. So when we do this calculation, we still get pi over 10 radians per second. And this one might make you feel a little bit weird. Wait a minute. That's exactly the same omega that we found for the person on the outside. Yeah. Because they're still going through the same angle in the same amount of time. In 20 seconds, both of those people have done a full circle. Doesn't matter the size of the circle, because we're just looking at the rotation. Rotation has nothing to do with distance away. So here's what's kind of crazy. On a merry-go-round, everybody is spinning around at the exact same velocity. Spinning around. They have the same angular velocity. So think about Earth. Let's not talk about Earth going around the sun, because that's not a circle. We actually travel an elliptical path around the sun. But let's just talk about the Earth rotating on its axis, right? What makes days, right? So everybody on Earth is traveling at the same angular velocity. We all do 2 pi radians in 24 hours. Not exactly 24 hours. Right? It's not exactly 24, but it's close enough. Okay, so if we were to take our 2 pi divided by 24 hours, that's our angular velocity. Right? So pi over 12 radians per hour. And that doesn't matter where you are on Earth. You can be in Tahoe. You can be in LA. You can be down in Australia. You could be, up near the North Pole, hanging out on an ice floe with some polar bears. Like, okay, it doesn't matter where you are. We're all moving with the same angular velocity. But we're moving at different linear velocities. People at the equator travel a much larger circle than people in Tahoe. People in Tahoe travel a much larger circle than people up in Alaska. So if you're up in Alaska, your linear velocity, due to the rotation of the Earth, is much smaller. But we all have the same angular velocity. Something came up in the chat. Let me double check this one. All right, so Joe, you said, isn't this theory of relativity stuff? Actually, no. this doesn't relate to the theory of relativity in as much as the fact that we're moving at different velocities does mean time will progress differently for different people on Earth. However, the differences in those velocities, we're so far away from the speed of light that it's negligible. Nobody would notice the difference in their time clocks because of that. So are there relativistic effects? Yes, they're minimal, but this has nothing to do with why theory of relativity is what it is. That's more just a consequence of the fact that the speed of light is constant in the universe. But if you're interested in that, take the physics sequence, the calculus-based physics sequence, and when you get to physics 208, you'll get to talk all about relativity. I'm actually teaching that this quarter, so in a couple months, or in about a month, I get to start talking relativity. Anyway, all right, so here's just a consequence. Like, think about it. We're supposed to be talking about triangles, right? Trigonometry, we're supposed to be measuring triangles, and yet we're off on this weird, crazy tangent talking about things moving around in circles. Yeah, they kind of go hand in hand. And in fact, you're going to see that most of what we do has nothing to do with triangles and has everything to do with rotation. All right, that's why I wrote down on the board. Remember that angles are a measure of rotation. All right, so let me just show you one more thing in terms of the velocities. That's kind of nice because there is a relationship between the angular and the linear velocities. So what I want to do is I want to bring back that relationship between the distance and the angle. Right? We had this formula that was S equals R times theta. And what I'm going to do is I'm going to divide both sides by time. You'll see why real quickly. All right, so on the left, we've got S over T, and on the right, I'm just going to rewrite this real fast as R times theta over T. Basically, I'm just factoring out the R. All right, so notice here, we've got an S over T. So that's a distance traveled divided by time. Well, that's our linear velocity. Of course, we've got R. R is still R. But then if you look at this other piece, we've got theta over T. So it's a change in our angle with our rotation over time. Well, that was our angular velocity. And so there is a relationship between linear velocity and angular velocity when you're traveling around in a circle. And it's V equals R times omega. And you can actually see that. I left this one up on the board just so we could look at that. Here was our angular velocity. Here's our linear velocity for somebody who was out on the outside of that merry-go-round. And notice that if you take omega and you multiply by the radius, so pi over 10 times 2 does equal pi over 5. So I bring this up because it's actually a faster way of finding your linear velocity. you don't have to find the circumference of the circle. You don't have to find the arc length that we traveled through. Well, all you need to do is take your angular velocity and multiply by the radius. So we could have, just at this point, once we got omega, taken pi over 10, multiply by 2, there's our answer. Fast. All right, so the other nice thing about this formula is that it looks a heck of a lot like the one that involved arc length and angle. And notice it's got the same forms. You've got your linear piece is equal to your radius times your angular piece. And if you go further, like if you take physics, you're going to learn about acceleration. Acceleration is your change in velocity with time. Well, there's also angular acceleration, and you're going to see that the same formula holds. That your linear acceleration, we call it tangential acceleration in the case of a circle. Your tangential acceleration is going to be your radius times your angular acceleration. It's going to follow exactly the same formula. All right, so hopefully that helps. And I forget who it was earlier asked if we were going to talk a little bit about velocities. This hopefully should help you with those problems that come up in the homework. All right, well, there's one more thing I want to talk about circles before we get to triangles. And I want to talk about the area. And specifically, I want to look at the area of a sector of a circle, of a piece of pie, basically. Right? If we don't have a full circle, but just a piece of it, I want to be able to determine its area. So here's a nice generic piece of a circle. And the question is, what is its area? Okay, so area of a circular sector. So let's put on the things that we know again. We're going to have some angle that we're going through. We're going to have some radius. And we'll go ahead and put the S here. That's what we've seen so far, the S, the R, and the theta. But now I want to know what its area is. Okay, so how about this? If it was a full circle, if we did a full circle, an angle of 2 pi, what would the area be of that circular sector? If I did one full rotation, how much area did I enclose?
The entire thing, like the
Okay,
entire
the
circle.
entire thing, the entire circle. So what's the area of a circle? What's the formula for it? Oh, don't make me go horrible dad math joke on you.
Isn't area pi r squared?
Yeah, it's pi r squared. No, pi's are round. Okay, sorry, that's bad math. Dad math. All right, so the area is pi r squared. Right. So if we did an entire rotation, so do an angle of 2 pi, we're going to get an area of pi r squared. So then the question is, what if we just do an angle of theta? What kind of area are we going to get? Well, here's how we're going to do that. We're going to think of theta as what portion of a full circle did we do? Because that's going to be the portion of the area that we get, right? Like if I do a quarter rotation, I just took that area, I cut it into 4s, and I kept one of them. So I've got 1/4 of it. If I did a 1/10 of a rotation, I'm going to get a 1/10 of this, and so on. So mathematically, what that means, we're going to set up a ratio. Let's set up a ratio of area per angle. So I'm going to get a full pi r squared if I do an angle of 2 pi. if I do a portion of it, if I do an angle of theta, I'm going to get some unknown area. But it's just a proportion of it, depending upon what proportion of the full rotation I just did. Okay, well, I'm just going to solve this for A. So I'm going to multiply by theta to both sides. So I'm going to get A is equal to pi r squared theta over 2 pi. And I can go ahead and cancel those pi's. These guys are gone. And so the formula that we get for the area of a sector of a circle is A equals 1/2 r squared theta. So I'm going to go ahead and box that as well. So if you ever want to know the area of a slice of pizza, all you got to know is how long are the slices, what's your radius, and what rotation did you go through in radians. And in fact, I'm just going to put like a really big in red in radians with some exclamations, and I'm going to point to all of these. All of these formulas in radians, not degrees. Okay, you want to be in radians. You may remember last time when I first introduced radians, I said they're much better mathematically. This is the start of why they're much better mathematically. The formulas are super nice, super easy when you're in radians. Okay, so you want to do all this stuff in radians, not in degrees. But luckily, we know how to convert from degrees to radians. Right? Just multiply by pi over 180 and you're good to go. All right, so we're supposed to be talking about triangles. We run into circle stuff. Okay, let's get ourselves out of the circle weeds for a little bit and let's look at triangle. Okay, so what I'm going to do now is introduce you guys to the trig functions. These are the tools that we use to do trigonometry. These are functions, just like other functions that you know, right? The idea of functions is you plug something in, you get something out. All right, these are trig functions. These are ones that are specifically designed to deal with triangle, but these are the players in the game of trig. Everything that we do is going to come back to these guys. All right. So let me introduce you to the trig function. And there are 6 of them. So here we go. All right, they are in no particular order. That's false. There's a reason I do this. All right, no particular order. There's sine, cosine, tangent, cotangent, secant, cosecant. So these are the 6. Sine, cosine, tangent, cotangent, secant, and cosecant. I'm going to bet that you've heard some of these before. We often run into them along the way in trig, like in geometry. Sometimes those terms are used in other places. Like we talk about tangent lines, which are lines that just graze functions and things like that. But these are our 6 trig functions. All right, now mathematicians, of course, are lazy. If you don't know this, mathematicians are lazy. And because we're lazy, we're not going to write out the entirety of these. We have abbreviations for each one. So instead of writing out sine, you're going to see just SIN. So like if you look at a calculator, a scientific calculator, you'll see a button that says sin. Well, that's sine. So cosine, of course, is COS. Tangent is TAN. I think you're seeing the pattern, right? We're just using the first three letters. So cotangent is cot. Secant is sec. But then we run into cosecant. And there's a bit of a problem with this. If we just use the first three letters, COS, well, that's reserved for cosine. So cosecant is the only one that we have to change the abbreviation from being the first three letters. And this guy, we write it as CSC for cosecant. All right, so that's how we're going to write them. We're not going to write out the full names. We're just going to use the three-letter abbreviations. But like I said, they're pretty easy. They're just the first three letters with the exception of cosecant, but CSC, yeah, okay. That makes sense. All right, so these are, now, like I said, they are functions. They are functions, which means we're plugging something into them. So what you're going to see when we write these out, you're going to see them written like f of theta equals sine of theta. I try to always put parentheses, at least at the start, to help you remember that this is a function. We're plugging something in. And what we're plugging in are angles. So angles go into trig functions. Now, if you ask me why, I'm just going to tell you because that's how they're designed. They were designed as functions of angles. And I'll show you that in just a second, like how they're defined. All right, so you're going to see that, but it won't always be written as theta. Like you might see something like y equals cosine of x. This x is still an angle, even though we're using the letter x for it instead of theta. Right? It doesn't matter. Whatever we're putting in there, it's an angle. So it could be a theta, an x, a t, whatever letter you want, but that's an angle that we're putting. Okay, so these are the 6 trig functions. So let me show you where they come from and how they were defined. Now, this is old. This is really old. This is thousands of years old. You can either thank or blame, depending upon how you feel about this. You can either thank or blame the Greeks, the ancient Greeks. They were the ones that came up with these and defined these 6 trig functions. All right, but what they all were defined as, they are all ratios of the lengths of sides of right triangles. That's how these things came about. So every triangle has 3 sides, right? Well, if you were to take those 3 sides and pair them up into pairs and make fractions of them, there are 6 different combinations that you can have. Hence the 6 different trig functions. So these are taking sides of triangles and putting them all together. All right, so here's how they were defined. Here's a generic right triangle. So right triangle just means that there's a right angle. All Now, if we specify one of the angles, so I'm going to go ahead and use, this guy is theta. I'm going to name the three sides. I'm just going to name them. The long side, that's the hypotenuse. So this guy over here, it's kind of a crazy name, hypotenuse, but that's the longest side of a right triangle, the hypotenuse. And the longest side is always the one that's opposite the right angle. Now, the other two sides, I'm going to call them adjacent and opposite, meaning it's either adjacent to the angle that we're curious about, or it's opposite the angle that we're talking about. All right, so hypotenuse, adjacent, and opposite. All right, well, if we have these, here are the definitions of sine, cosine, tangent, and all of the other trig functions. Sine, this is the opposite divided by the hypotenuse. So if you take that opposite side's length and you divide it by the hypotenuse, that gives you your sine. Cosine is the adjacent divided by the hypotenuse. Tangent is the opposite divided by the adjacent. Cotangent is the adjacent divided by the opposite. Secant is the hypotenuse divided by the adjacent, which leaves for cosecant the one other combination, which is the hypotenuse divided by the opposite. So again, you ask me why, you're going to get the total dad answer. Because this is just how they decided to name these things. All right, so if you've got a right triangle and you know the lengths of the sides, it's actually really easy to determine the 6 different trig functions. So let me show you. Here's a right triangle with lengths. All right, so let's do this one. And I will tell you that the lengths of these three sides are 5, 12, and 13. You probably are really familiar with the 3, 4, 5 right triangle. If the two side lengths are 3 and 4 and the hypotenuse is 5, you get a right triangle. 5, 12, 13 is another one that has nice integer sides, whole number sides. There are a bunch of them, but there's another pretty well-known one. All right, so let's specify an angle. Let's call this guy alpha, just for the hell of something different. And let's calculate the 6 trig functions for alpha. All right, so we're going to have sine of alpha. So the sine of alpha is the opposite over the hypotenuse. So the opposite side, opposite alpha is 12. And the hypotenuse is 13. So sine of alpha is 12, 13. Cosine of alpha, that's the adjacent side divided by the hypotenuse. It's 5 over 13. All right, so tangent of alpha is opposite over adjacent, so that's going to be 12 over 5. Cotangent was adjacent over opposite, so that's 5/12. secant was hypotenuse divided by adjacent, so that's 13/5. And then cosecant was hypotenuse divided by opposite, so it was 13/12. So it really is this easy. Given a triangle, you want to know the 6 trig function values for one of the angles. All you got to do is remember these relationships. Now that might feel a little daunting because there are 6 of them and it's not, which one goes where?
Hey, Bruce, I got a question.
Yeah, sure.
Are the cotangent, secant, and cosecant just the inverses of the sine, cosine, and tangent?
I'm going to just change one word in that and then say yes. They're the
Reciprocal.
reciprocals. And I hate to get math technical, but you're totally right. Because when you say inverse there, you mean multiplicative inverse. We never say that, right? But it's going to matter later because there are inverse functions to the trig function. But yeah, no, they are just reciprocals. And in fact, that's one of the things that you can use to help you remember this, right? Look at tangent and cotangent. It's the same thing, just flipped over. Cosine and secant, same story. You just flip this over, you get the other one. And the same thing with sine and secant. And you can even see that specifically with the numbers, right? 12/13, 13/12. 5/13, 13/5. 12/5, 5/12. So that's definitely one of the nice things about these is you don't actually have to learn all 6. In fact, you can just learn the first 3. If you learn the first 3, you can get the other 3 just by flipping them over. All right, so a Bruceism. This I say this. I don't know if other people do. I call sine, cosine, and tangent the big 3. Because if you know the big 3, you know the other 3. And the big 3 are the ones that we tend to use a lot. So let me actually take what we have just been talking about here and write it down, kind of formalize it. And this is what we know. We've got that the cotangent is the same as 1 over the tangent. That's what it means to be a reciprocal, right? 1 over. We have secant is 1 over cosine, and cosecant is 1 over sine. And these are always true. Doesn't matter what the angle is. And so when you have an equation that's always true, we call those identities. I don't know if you remember that name, but an identity is an equation that's always true. Doesn't matter what value you plug in for the variable. And so these 3, we actually call these the reciprocal identities. So if you're like reading the book, they make reference to, or you hear me say reciprocal identities, that's what I'm talking about. But it makes it so you just need to know the first 3. So that's kind of cool. It makes it a little bit easier. Instead of remembering all 6, you just remember the first 3. All right, now let me help you remember the first 3. Because if all we need is the first 3, well, let's get that. So there's a nice little mnemonic device. Mnemonics, those are those like little sayings that you and then remember forever. Like for example, I remember when I was taking biology and I had to learn the taxonomical, breakdown, kingdom, phylum, class, all that good stuff. My mother, who was a microbiologist, but like went to college in the 50s, so this is hers. She was like, kids put cream on fat green spiders. Okay, I remember this now over 30 years ago, because it's a silly mnemonic device. Kids, kingdom, put, phylum, cream, class, on, order, fat, family, green, genus, spiders, species. Okay? So kids put cream on fat, green, spiders. When I actually got to high school and took biology, I had a dirty old man as a teacher, and so his was K puts candy on Fred's G string. You notice that that one rolls off my tongue a little bit faster. So it definitely it struck a bigger mark, but that's a mnemonic device, right? Okay, so there's a good one for sine, cosine, tangent. And this is another one that I learned forever ago when I first learned trig some point in the 1980s. Yeah, that's how old I am. And it's called Sohcahtoa. Which inevitably gets perverted into like Sohcahtoa or something like that. Sohcahtoa. And notice what this is. The first letter tells you which of the big three: sine, cosine, tangent. The other two, those are the sides in your ratio in order top to bottom. Opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. All right, so Sohcahtoa is a great little way to help remember the big three. So then you can just flip them over to get the non-big three. I had a student now many years ago, over 15 years ago for sure, probably pushing more like 20 years ago, who was from Singapore. And she told me that they actually learned a different mnemonic device. And so now I share this one as well. But she said this is how they remembered. Their little saying was, "Oh hell, another hour of algebra." For many of us, yeah, that sounds about right, right? But it's, "Oh hell, another hour of algebra." And I guess that's probably an exclamation. But I don't know if you can see it, but here's your opposite hypotenuse, adjacent hypotenuse, opposite and adjacent. Right, so, oh hell, another hour of algebra. If you remember in this order, sine, cosine, tangent. Okay, so remember the big three. And if you got the big three, you can get the other ones using the reciprocal identity. Okay, now I do want to point out that it's super important that you know which angle we're talking about in the triangle. Okay, let me actually bring back that 5, 12, 13 triangle that we were playing with. Let me redraw that. So we had 5, 12, 13. And these values that we found down here that I still have written at the bottom of the board, those were for alpha, where alpha was the angle that was down over here. Now, if instead we had looked at the other angle, let's call this beta. I want you to notice that we're going to get different values for the 6 trig functions of beta. Right? So like if we were to look at, say, sine of beta, so now we need to go to the side opposite beta. The side opposite is now the 5. The hypotenuse is still 13. So the sine of beta is going to be 5 over 13. The cosine, well, it's now adjacent side is the 12. And that's 12 over 13. And then tangent, the tangent of beta, if we do opposite over adjacent, that's actually 5/12. And now that we have the big three, we can get the other ones really fast. Cotangent, we're just going to flip over tangent. Secant, we're going to flip over cosine. And cosecant, we're going to flip over sine. I'm going to get my shadow out of the way. Maybe you can see it a little bit better. But notice that they're not the same, right? 5/13 versus 12/13. 5/12 versus 12/5. 13/12 versus 13/5. They don't match up. However, maybe you do see a pattern here. Anybody see similarities between the red list and the black list? All right, so sine and cosine are opposites, says Ivy. Samuel says, notice that the numbers are still all 5, 13, and 12. Yeah, those are both some really good patterns. Let's start with the 5, 13, and 12. All of them, doesn't matter which one from this triangle, have values of 5, 12, and 13 somewhere in there. And that's because those are the lengths of the sides of this triangle. And if we define all the trig functions as ratios of the sides of the triangle, we should expect that we're still going to see the 5, 12s, and 13s even in the other set because they're coming from the same triangle. So yeah, definitely there's that pattern. And then the other one, who Ivy put up there, notice that the sine and the cosine, they swapped. Right? Here was the sine, was 5/13. That was the sine of beta. That's the same as the cosine of alpha. And similarly, the sine of alpha is the same as the cosine of beta. So good patterns recognition there, that the sine and the cosine swapped. But let's go one step further and notice that the same thing happens with other pairs. Secant and cosecant, this should come as no surprise to anybody, but secant and cosecant do the exact same thing. Here's our secant of beta is the same as the cosecant of alpha. And we had that the secant of alpha and the cosecant of beta were the same. But that shouldn't surprise you that the same thing happened with secant and cosecant. Because if they come from just flipping over sine and cosine do the swap, then secant and cosecant should as well. But even more, notice tangent and cotangent, they do the same thing as well, right? The tangent of beta is the same as the cotangent of alpha. And then the tangent of alpha is the same as the cotangent of beta. So I tried to color code them. I don't know how well those colors are coming out. But you can definitely see that there's this exchange. Sine switches with cosine. Tangent switches with cotangent. Secant switches with cosecant. Okay. This is how they get their names. This is how these things got named. So let's just start with sine. Notice that what happens with sine, if you look at the other angle in the triangle, it becomes the cosine. The tangent of the other one becomes a cotangent. The secant, that are now erased here, secant becomes the cosecant. So the fact that there were always co-functions, remember what co means? Right? Like we were talking about coterminal, so they share, right? So sine and cosine, they actually share the same values. The sine of one is the cosine of the other in a right triangle. Okay, so interesting for sure, but by the way they were defined, has to be true. It has to be true that in a right triangle, the sine of one becomes the cosine of the other. All right, now we're going to formalize this as well, because that's a nice little pattern. But before we get there, I want to remind you something about the angles. Anybody remember what's true about alpha and beta in a right triangle? Like what those two angles add up to always, no matter what?
90.
Okay, so they add up to 90 degrees. What would that be in radians? How many radians is 90 degrees?
Pi over 2.
Pi over 2, awesome. Okay, so we got alpha plus beta is equal to 90 degrees, or, because I want to get you guys thinking radians, it's the same as pi over 2 radians. So let me just kind of put that in a box to remind you. Or if you've not seen that before, just a fact for you. The two angles that are not the right angle in a right triangle add up to 90 degrees, or pi over 2 radians. Okay, so because of this fact, and the fact that the co-functions basically just swap, we can create what are called co-function identities. So just like we had the reciprocal identities, statements that are true regardless of the angle, co-function identities, it's the same deal. These are going to be true regardless of the angle. So what we know is that the sine of theta, be our first one, sine of theta actually equals the cosine of pi over 2 minus theta. And we can actually make a similar statement for the cosine. The cosine of theta is the same as the sine of pi over 2 minus theta. The pi over 2 minus theta, that's the other angle. Right? That would be, call one of these angles theta and solve for the other. And you get pi over 2 minus theta. All right, so we've got those for sine and cosine, but then they are also true for all the rest. So you're going to get the tangent of theta is the cotangent of pi over 2 minus theta. Cotangent is the tangent. And then secant and cosecant follow suit. So this was just formalizing. This was putting into math speak the facts that we just saw. Right? Like when Ivy said, hey, the sine and cosine swap, what she saw was these first two things, these first two statements that I wrote. But this is just a real mathy way of writing that same thing. So some of you are probably thinking, well, Jesus, why are we going into this real mathy technical definition when like we see the pattern and we know what's going on? Well, remember what this class is for? I'm training you for calculus. And when we get to calculus, we get really mathy. We try to describe everything mathematically in proper math terms. So I'm teaching the language of math, and we're using trigonometry to get there. All right, well, anyway, so we've got these identities as well. So notice that in a right triangle, if you know the trig functions for one angle, you know them for the other, because they come from the same place. All right, so what? Who cares? Why do we care about these trig functions? It's silly. You give me a right triangle with lengths, I can just plug in those lengths and get these things. So what? Why do I care that it's the sine, the tangent, cotangent? Well, the so what, and there's a lot of so what that we're going to learn over the course of this class. But I want to start with something just like a real easy question that we could answer making use of these trig functions. All right, so here's this really simple, really basic question. Suppose that we're out walking in the meadow and we come across a tree. So there's a big old pine tree, and we want to know how tall it is. But we're not very good at climbing trees. So we can't actually like climb to the top and drop down a tape measure. But I'm curious how tall is it? But what we do have, so let's say we're over here, we do have the ability to measure an angle. All right. So, and believe it or not, it's not hard to construct a tool that would do that. All you would need is a protractor. You can just buy a real simple protractor at like Office Depot for like 50 cents or something. So all you need is a protractor. Drill a little hole right in the center of the measurement there. Take a piece of string, put it through that hole, you know, tie a knot so they can't slide through it anymore, and then attach a weight to that string. That weight is always going to be pointing straight down. So all you have to do is tilt your protractor until you're looking at the top of the tree. When the string comes down, you can read off it and you can measure that angle. So it's pretty easy to do. All right, so here's what we do. We measure that the angle to the top of that tree, right here, let's say is 58 degrees. Now, because this is on the ground, and we're going to assume that it's level ground, so this is a right triangle, we measure this distance, and we find out that this is 4.5 meters. Okay, so we're 4.5 meters from the tree, and we measure that angle to be 58 degrees. And I want to know, what is the height of this tree? So it's a really easy question. How tall is that tree? And it turns out we can get the height of that tree without climbing the tree if we use some trig. All right, so here's what we're going to do. We're going to think back to the big three. Let's think sine, cosine, and tangent. And let's think of those in terms of this guy, 58 degrees. So in terms of the opposite adjacent hypotenuse, the hypotenuse is this pink side. The opposite is the tree. That's the opposite. And then the blue side, the ground, is our adjacent. Now, what we want to pick the trig function that involves the height of the tree, thing that we're trying to figure out, and one more side whose length is known. So in this scenario, the length that's known is this 4.5 meters, or the adjacent side. So I'm immediately going to pick one of the ones with adjacent. So I'm not going to use sine. Well, the side that I'm curious about is the opposite. So I want a trig function that involves opposite and adjacent. All right, so which of the big three is that? Is it sine, cosine, or tangent? All right, cool. Thanks, Dylan. Typed in the chat box tan. So we're going to use tangent. So here's what I know. I know the tangent of 58 degrees is going to equal the opposite side. Let me call it x divided by the adjacent side, which is 4.5. So if I want to solve this for x, I just have to multiply by 4.5. So I'm going to get x is equal to 4.5 times the tangent of 58 degrees. And this is where this is going to come in handy. Because your calculator knows how to do the trig function. In fact, every good scientific calculator will have a button that says sin, one that says cos, and one that says tan. I don't know if you can see it on mine. No, because it's trying to focus over on this side. All right, well, anyway, there's sine, cosine, and tangent as little greens above there. So I've got sine, cosine, and tangent. Well, let's get those values. Before we actually do this computation, though, word of warning. And I'm going to warn you about this. We're still going to make this mistake. That's all right. It happens to everybody. Even happens to me sometimes if I forget. You got to make sure you tell your calculator if you're using degrees or if you're using radians. Because every good calculator will know how to do both, but you have to tell it. You have to make sure that you're in the right mode. Now, how you change that depends on your calculator, but it should definitely tell you. Like I've got a TI-89, and down on the bottom it says rad. It tells me right now it's in radians, so I know I need to change that. So I'm going to go into mode here and change it from radians to degrees. So again, depending upon your calculator, which type you've got, you change it in a different way. But now it says day. So it knows I'm in degrees. So make sure you tell it whether you're in radians or degrees, and then you can go ahead and do this calculation. So we take 4.5, we multiply by the tangent of 58, and I get 7.2 and some other trivial numbers after that. There's a 0 and some other stuff. So this is around 7.2. So what we know is that that tree is around 7.2 meters tall. And never once did we actually have to climb that tree. All right, this is something that's done a lot, actually, when we humans want to figure out how tall things are, how big things are. Sometimes we don't actually literally measure them. We measure other things, and then use trig to help us get there. So if anybody's interested in going down the path of being like a surveyor or engineer, this is the kind of thing that's practical usage of trig. So that's why these trig functions even came about, was to help answer these kinds of questions. Because instead of knowing that side specifically, if you know one of the other sides, doesn't matter which one, and you know an angle, you're good to go. So believe it or not, when it comes to solving triangles, when you solve right triangles, you pretty much have everything you need to calculate the other sides if you know one of them. There's one more fact about right triangles that I do want to mention just for completeness, but you guys also know about this, and that's the Pythagorean Theorem. By this point in your math life, you've probably seen this so many times that it's not even a thing anymore. But on the off chance that has slipped through the cracks for you, if you're given a right triangle, and we label these sides length A, B, and C, where C is the hypotenuse, then the Pythagorean theorem tells you that there is a relationship between them, and that is that a squared plus b squared equals c squared. So this is another way that you can get lengths. If you know two sides, you can get the third side using Pythagorean theorem. But if you only know one side and an angle, you use the trig functions. You only ever have to use one of the big three. And which of the big three to use? It depends on what you're working. All
I
right.
have a quick question.
Yeah, go for it, Eddie.
I got, when we were doing tan 58 degrees equals x over 4.5, how do we know that x equals 4.5?
So x doesn't equal 4.5. It's 4.5 times the tangent of 58. But if the question is, how did I know that this was 4.5? I made that up. I was just saying that that would have been a length we could have measured.
Oh, okay, I think I just misread it. I didn't realize they were being multiplied. I thought those were two separate statements, so to speak.
Oh,
Thank
okay.
you.
That was just solving this equation, right? Like if I multiply both sides by 4.5 to get rid of the fraction, it turns it into 4.5 times tangent of 58. Does that make sense? See where that's
Yes.
going from?
Yes, thank you.
Okay, yeah, you're welcome. All right, so hopefully this also gives you a little justification for why we care about the trig functions. There is a use for them, specifically coming from measuring triangles, hence trigonometry. All right, so I just want to show you a couple more things before we go. Since I didn't take a break or anything, we're not going to go all the way to 1250. We'll cut off just a little bit. But I do want to show you just some special angles and the trig values for those special angles. Because there are some nice right triangles. You may remember some point in time, you learned about 30, 60, 90 right triangles, or 45, 45, 90 triangles. So I'm going to call these the nice right triangles with the nice angles. So the first one, let's look at the 45, 45, 90. So it's called the 45, 45, 90 because those are the angle values. There are two angles whose values are 45 degrees, and the other one is 90 degrees. It's the right angle. Okay, so this is in degrees. In radians, if you were to convert these to radians, multiply by pi over 180, this is the same as pi over 4. And then the 90 was pi over 2. So in radians, it'd be pi over 4. Okay, now notice first with the whole co-function thing, since both of these angles are identical, it's kind of silly to do the sine of one and then the sine of the other because they're the same list. Okay? But check this out. Geometrically, this is half of a square. This triangle right here, if you were to just duplicate it, that thing's a square. Because you'd have 45 degrees, another 45 degrees, that's a right angle. All those things are right angles. So this thing comes from a square. So what I'm going to do is just give those things the same length. We'll just call them length 1. All right, now for the Pythagorean theorem, we can actually calculate this third side. Because we're going to get 1 squared plus 1 squared equals c squared. So that's 1 plus 1, which is 2. So we just take a square root and we get the square root of 2. So we know all three sides, which means we can get the trig function values. So from this, we know the sine of pi over 4, it's equal to opposite over hypotenuse, which is going to be 1 over root 2. The cosine of pi over 4 is actually going to be exactly the same. It's also 1 over root 2 because these two sides are the same length. All right, the tangent. Well, it's opposite over adjacent, which is 1 over 1. So for the big three, we get these values. Now, I do want to point out, I know I just changed the sine and cosine, and some of you are probably like, whoa, where the hell did that come from? These I rationalized. Don't know how much you remember about rationalizing, but if you've got a radical on the bottom, you can just multiply by that same radical. So we would get here the square root of 4 on the bottom, and the square root of 4 just becomes a 2. So that's what I did to change this to root 2 over 2. All right, so for the big three, for 45 degrees or pi over 4 radians, there they are. Sine and cosine are both root 2 over 2, and tangent is equal to 1. And if you want the other three, you just flip them over. So cotangent is going to be, well, if you flip 1 over, you get 1. Secant, you flip this over, you get root 2 over 1, which is square root of 2. Cosecant, similar. So that's one of the nice angles, pi over 4, 45 degrees. Because it comes from a nice triangle, just half of a square, we're able to get these ratios really quickly. All right, so there's your 45, 45, 90. Now, the other big triangle is a 30, 60, 90. And the 30, 60, 90, kind of similar deal here. But it looks like this, where the angles are 60 degrees and 30 degrees. So there's our 30, 60, and 90. Okay, so we want to do the same thing. We want to be able to figure out what the three sides are so we can calculate the trig functions. And this one also comes from a nice shape. If I were to copy this and put it over here, so that this is another 60 degrees and that's another 30 degrees. This guy is an equilateral triangle. All of the angles are exactly the same, 60 degrees, 60 degrees, 60 degrees, because it's two 30s that we're at it. So that's an equilateral triangle, which means all of the sides have the same length in the big triangle. Okay, so here's what I'm going to do to label these. I'm actually going to make this side on the bottom be 1. Trust me, it's going to be nice that that's 1. Because that's half of the long side. So that means that this long side has length 2. All right, well, I've got 2 sides, which means I can get the third side using the Pythagorean theorem. So let me erase this piece, and let's get this third side. I'll call it A. We'll use the Pythagorean theorem. So A squared plus 1 squared is going to equal 2 squared. So A squared plus 1 equals 4. a squared equals 3, or a equals the square root of 3. So there are the 3 sides of this triangle. And now that we have those, we can get sine, cosine, and tangent for these 2 angles. So let's start with the 60 degrees. So the sine of 60 degrees. Sine is opposite over hypotenuse, so that's √3/2. The cosine of 60 degrees. It's adjacent over hypotenuse, which is 1/2. And then the tangent of 60 degrees is adjacent over hypotenuse, adjacent over, opposite over adjacent. So √3 divided by 1, which is √3. And again, that's as far as I need to go, right? Because the other 3 we'll get just by flipping them over. Cosecant is going to be 2/√3. Secant is going to be 2/1. Cotangent is going to be 1/√3. All right, so there are your sine, cosine, and tangent of 60 degrees. So let's get the 30 degrees. But this time I'm going to mix it up. Let's change it to radians. The radian values for these, again, 90 was pi/2. 60, that's pi/3. And 30 is pi/6. Again, if you multiply by pi/180 and reduce, you'll get those. So what I'm going to do for my last list here, I'm going to do it for the 30 degrees, but I'm going to write it as pi/6 just for the practice. So I'll have sine of pi/6, cosine of pi/6, and tangent of pi/6. And let's get those values, but again, we'll use the right triangle. So that's this angle. So sine opposite over hypotenuse is 1/2. Cosine adjacent over hypotenuse, √3/2. Tangent opposite over adjacent is 1/√3. But we didn't actually have to go back to the triangle if we had just remembered the co-function thing. Since we're in the same triangle, we just have to swap. So sine became cosine, cosine became sine. Well, the cotangent, which was 1/this, became the tangent. Rationalize, just FYI, this is square root of 3/3, if you were to rationalize that. But there you go. There are the big 3 functions for pi/6 or 30 degrees, which means you get the other ones just by flipping them over. All right, so these are just some special angles. We're going to see these angles a lot. In fact, we're going to practice a bit with them next time. They're going to be a big part of what we do, these specific angles. Okay, well, anyway, so there you go. There are the 6 trig functions. If you know the sides, you just get them by looking at the ratios. And we're going to start seeing lots of patterns, lots of relationships between these functions because of how they're defined. All right, and that's what we're going to do next time. So at this point, I think we're going to go ahead and wrap it up. We're going to call it a day. Just some things to remind you. The first homework set is due Monday night at midnight. So don't forget about getting in there and working on that. First homework sets, there's 2 of them, right? The 7 ones. So make sure you get in and work on those. But other than that, have an awesome weekend, and I will see everybody on Monday.
Thank you.
Thank you.
Thank you.